And we're starting, let's see, this is the 7th week, is that right? I think it is, the 7th week of the semester. We're listening to the Rolling Stones, and that was I Hear You Knocking, I believe was the title of that. And as we start this 7th week, several things. One, I return lab number 7, and that is the lab that you used to create a random sample of 30 countries. Several comments I'd like to make on that. You should have addressed the homework assignment for the first chapter in probability. I'd like to talk about that. I need to talk about Lab 10. Finish up some discussion about Chapter 11, and I have a hunch that that's going to take much of our time this morning. And the first thing, if this is going to function well enough here, I'd like to point out I entered the data for Lab 10. I think it was Saturday morning. So I'll show you where that is in the website, and you're going to need that data. You will have to enter this data into StatGraphics to do the lab, and so we'll get to that in a moment. I would like to have you also turn to page 283 in the text, and that would be the first thing. And as we go to the board, while all waiting for the computer to cooperate with me, I'd like to look at the adjustment we made to a standard deviation for a population, given that StatGraphics instead gave us a sample standard deviation. Now this is in Lab 7, and it's going to be very important in Lab 10. So as I go to the board in this, Jennifer, the argument is, again, just a reminder, that S as a sample standard deviation, if we look at it conceptually, is this formula. Now when you ask StatGraphics to go ahead and do a numerical analysis and you get the standard deviation, it's using this formula, even though we have a population of data. Now the first thing to note, if I have a sample of data, this is the correct formula and I do not have to adjust. One more time. If I have a sample, like 30 countries, and I calculate the standard deviation, no adjustment is necessary. But if I'm calculating the population standard deviation for the 222 pieces of data I have, I'm going to use big N here, indicating the population size. This is the formula that should be used. Now the difficulty is that the formula on the top was used by StatGraphics. So you have to adjust that value of S given, which was a population, supposed to be a population value. And so in essence, I had you doing this multiplication. Because if you multiply S by the square root of n minus 1, the square root of n minus 1 cancels with this square root of n minus 1, and this becomes the denominator, and now you have this. So this gives you, for StatGraphics, the correct value. And I believe that came out 10.89. In general, well, I'll even make it stronger. You can never take a sample value for a sample. Otherwise, you actually have a sample of 30 countries. You can never take that value and generate a population value out of it. It's not going to happen. So you can't take this for a sample of 30 countries and generate a population value from it. The only thing that you have is a problem with StatGraphics whereby an incorrect sample statistic was calculated for a population. And I had several people try to take and make the same adjustment for the 30 values when you had S. There's no adjustment you do there. Okay, so that's one of the most important concerns I have regarding the lab. Now, in Lab 10, your argument is that you have now, and let me, I guess at this point, what I'm going to do, Jennifer, is go back to the document cam. This is the video-based home page. And I'd like you to note, as I scroll down just a little bit here, and then I bring this over to the right side, I have a Lab 10 data file for fall 2008 for you. And that was created this weekend. And I took your values you gave me, and I'm going to just click on this. And when I do that, what comes up is a list of data. And I think I can probably go about there, yes. And then scroll up a little bit. Mean and standard deviation. Now you're going to have to enter these. I didn't make this a file for you that you can just bring across. I want you to enter this data. Now, comment, I want you to enter it to the nearest hundredth. So you're going to have to round off the means to the nearest hundredth. The standard deviations I want brought in as they are. Okay, as we come back and look at this data set, you'll note that there's a fairly large number of values. This includes some work that was done this summer. Okay. And if I scroll down now, I believe we have a total of 57 means and 57 standard deviations. So you're going to have to enter these 57 means and standard deviations into StatGraphics and create a data file. Again, round off the means to the nearest hundredth. And also have somebody proofread the file you've created. And I would suggest somebody check to make sure that they agree with your rounding. That will be the audit I do. Otherwise, if you have the correct 57 means, then when I ask you to get the standard deviation of those means, which I'm going to call S sub x bar, I'm going to go to the board now on that, S sub x bar will be the same for all of you. Now, if I find a discrepancy in that S sub x bar, I'll go back and look at your means and hunt for the error. If there's an error, it costs you 20%. So take time to check your work. Now you know what the theoretical value for sigma sub x bar is supposed to be. That's supposed to be the sigma you calculated in lab number 7. That was supposed to be then divided by the square root of the sample size. So this is about 10.89, I believe. Somebody can check me in that. I think there's a digit or two more. But that's in the lab I just returned to you. And if you adjust it, will somebody give me the corrected value if I do not have it correct here? Anybody have that? Lab 7 just came back to you. Check Lab 7. You were supposed to adjust that value. It's in your discussion question number 1. Who has it?
I have 10.981.
981. I reversed the digits. Okay? 981. Thank you. Do we have confirmation in that? 1 confirmation. 2 confirmations. Okay? Now, what is the sample size? 30. Doesn't have a thing to do with the fact I have 57 means. And that is where, if you are not careful, and you do not take notes right now and read the notes when you do the lab, that you'll make a very serious error. This is divided by the square root of 30, not 57. And if past performance is any indicator, I will have somebody, in spite of this comment, turn this lab in and use the square root of 57 and lose a half point. Now, what does this value come out as? It's very close to 2. We've talked about this earlier. I believe it's a 2.00. Will you do it on your calculator, please? Let's get this value correct. This is what you're going to reference in Lab 10 in your discussion questions. This is worth 1-letter grade in terms of Lab 10, to the extent that if you don't get this set up properly, it's going to cost you. So what do you get? 2.00? What's the third digit out of curiosity? Okay. Now, I have no idea what S sub x bar is. I did not enter the data yet. So I don't know how it's going to relate. But your S sub x bar that you're going to make a comparison to should be compared to 2.004. Now, what do you anticipate? A value smaller? Theoretically, it should be equal or larger. What's your argument? You should be able to make that argument right now based on the first 6 weeks of the course.
Larger because we're moving the extreme data values from our sample set. We're more likely to get more moderate ones.
Okay, we are. Okay, I'm hearing the response that we would get more moderate values of x bar. We would avoid the extremes. What should the impact of that be on S sub x bar? And think carefully. I heard very quietly, smaller. And that's the correct answer. If you do not have the extremes and the far ends of the curve, then your standard deviation is measuring a smaller spread and should be a smaller value. So S sub x bar, I anticipate being smaller than 2.004. Now, what am I using to justify the statement that I don't expect extreme values? What do I know about this distribution of these sample means? Chapter 11, title of Lab 10. Very well stated. The central limit theorem. We've talked about it from week 1. What does it say? The central limit theorem.
So ideally, you 60% of your data within what standard deviation of your...
Oh, to think of it in terms of an interval would be the empirical rule we could invoke, but you're jumping ahead a bit on me. Central limit theorem. You told me about it in Lab 7 in some of your write-ups. We've talked about it for 6 weeks. It says that if n, little n, is sufficiently large, and sufficiently large is going to be what value for us? 30 or more. Then what's true? Longer, louder, Candace? Okay, the mean of this distribution of x bars will equal the mean of the original distribution. But there's a more important statement before you get there. It is normally distributed. X bar. So the then for this statement is that X bar, and we use the phrase approximately normally distributed. The larger the sample size, the better the approximation. Is approximately normal with this mean. Now this goes back to the statement I was just given. The mean of your original distribution, which I'm going to call mu sub x. And here is the issue that the standard deviation of this distribution of x bars is the original standard deviation divided by the square root of the sample size. And this is true for any shaped distribution. So I've got a bell. And now, going back to Sean's statement, if I think of this bell and I take plus or minus 2 standard deviations of the mean, 95% of all my means are in that interval. Now what was mu? Roughly, you have lab 7 in front of you. Your mu is what value? All you have to do is look. It's in discussion question 1, lab 7. Look at it, please. 21.6985. So we would have 21.699. I've been talking about it roughly as 21.7. Daniel's correct in his value. And we are saying that this sigma sub x bar is about 2. To the nearest hundredth, it is 2. Take 2 standard deviations, you're at 4. So add and subtract 4 to this 21.7. So I'm, in essence, saying 21.7 plus or minus 4. Now that's everything to the nearest hundredth. So what is the range of my x bars that I expect to get under this normal distribution 95% of the time? Well, I can subtract 4 and get 17.7. I can add 4 and get what? 25.7. Sorry. And 95% of my x bars are in that range, correct? That's the argument. So am I going to get something in the extremes very often? No. Let's come back to the document, Cam. Okay, let's see what we've got here. Now these are 57 values. So how many out of that 57 would I expect to be outside this interval I just created? About 2 to 3, agreed? Otherwise, if I had 100, I'd only expect 5 of them. I have a little bit more than half that. So we expect somewhere around 3. Okay, let's see what we have. Okay, I have a 28.48. That's one that's outside, correct? So I'm going to try moving this up so it's not so jerky. We have 1. Still okay. 1. It appears I have only one value out of these 57 that's outside the interval. Is that, are you seeing the same thing? Let's go down one more time. Now, I didn't see anything in the high part, and I need to be under 17.7. And I don't think I saw anything there, but let me bring it down this way. Okay, and then let me bring it down again. We're looking for something below 17.7. I need to relocate the mouse. 17.7. That's it, right? So I have 1 out of 57. And that's my argument. Now, I would have been not surprised if I'd had 2, maybe even 3. As it turned out, I have 1 less than I would have anticipated. But my point is, you don't have these large values. So if we don't have these large values, S should be, S of x bar, should be lower. And if you get a lower value, should you be surprised given that we have a bell-shaped distribution? The answer is no. Okay? Your mean might be skewed which side? The mean of the means. X bar bar. Because you're going to be asked to do that in Lab 10. We have one data point that is larger than we expect to get and nothing to balance it on the left side. So if we go to this interval I have again, Jennifer, up here, I'm to the right side with the value, correct? But not below. What is the impact of then an extreme on this side? What's going to happen to the mean? Potentially. Goes to the right, it's going to be potentially larger than this, representing the skewing, because the mean is sensitive to a large value, which is outside this 2 standard deviations. What might we expect in the argument that we're supposed to have a bell-shaped distribution when I do the histogram? If I see any skewing, which side might I expect to see it? To the right, because of the high value. Now, before you start, you have a pretty good idea of what you should expect to get, and you should be in a position now to do the discussion questions in Lab 10. And I would encourage you, since Lab 10 relates so directly to Chapter 11, that you go ahead and look at Lab 10 tonight. Get this data entered, get your histogram, get your summary statistics, and see if you're getting what you expect. So we can discuss that while it's in your head. Now I ask you to go to a page in your book a few moments ago. I'm going to come back center, and we're going to go to the document cam in a moment. The particular distribution that we have for our birth rates, we said is skewed to the right and bimodal. On page 283 in figure 11.5, there is a distribution which you should recognize out of your background in intermediate algebra. Now, this distribution is only being shown in the first quadrant. It is an exponential distribution, e to the minus x. Y equals e to the minus x. And you are told that this distribution has a mean of 0 and a standard deviation of 1 for this particular exponential function if you read the information provided just above this set of diagrams. Now, at the very bottom of the page, you find a reference for these 3 diagrams. In diagram B, this is a mean taken from 2 observations. So your sample size is 2. Let's come off there for a moment, Jennifer, so I can try to get the book and the camera aligned better. There we go. So diagram B, n equals 2. Then C, we go to n equals 10 observations. And at 25, notice how this is centered at 1, which was the mean of the original distribution. And of course, that's what the central limit theorem is telling you, that you're going to have an approximately normal distribution if n is 30 or more. Now, the current language is sufficiently large, and 30 traditionally was the break point. David Moore talks about simulations and computers where 40 is used to a better result. We're trying to verify the central limit theorem, not prove it. We're trying to verify it in Lab 10. You're going to have two histograms you're going to compare. The original that you've done 3 times at this point. And may I remind you, for those of you who did not scale the horizontal axis correctly, I will be looking for the boundaries to match up to the bars, and you should have 7 or 8 bars or intervals or classes for the population of birth rates. You have a sample of 57. 2 to the 6th is 64. So 6 would be an appropriate choice for the number of intervals for your distribution of x bars. You're going to compare those two histograms. Hopefully the second one is what? Bell-shaped. Now, we on the board last week talked about how many possible sample means we could have. So I hope you understand that if we get anything close to what the central limit theorem is saying, we're going to be very fortunate. We would be up to 10 to the 36th power, roughly. Okay? And we don't even have 100 sample means. Any question in that? Because you're in a position to start working on Chapter 11, homework, and Lab 10, that should be something you have done this week. And I'll be entertaining questions on the lab and the homework tomorrow from Chapter 11. Okay, hopefully that says enough about the lab that you need to get started on. Now, you had a homework assignment in Chapter 10. Are there questions on the homework in Chapter 10 you would like to address? Chapter 10. Claire?
48.
Okay, number 48. Could you give me a page number, please? 268. 48 on 268. Okay, this is talking about a random number generator. This is number 48 on random numbers. And of course, as we come off there for a moment, just reminding you that you did this in Lab 7 using stack graphics as a random number generator, but there you had numbers between 1 and 225, I believe. Here, we want to generate random numbers between 0 and 2, correct? And you are told that the density curve is between 0 and 2 and has constant height. What is that telling you as we come off there? What kind of distribution? Okay, it's continuous. I agree with that. What else is it telling us? Constant height. Okay, it's going to be rectangular. How about uniform? You did a discrete uniform in Lab 7. This is a continuous uniform in this problem. Now, what is the characteristic of a density curve for a continuous random variable when we talk about the area under the curve? Okay, it must be 1, agreed. And if I have a rectangle between 0 and 2, that has to have an area of 1. What must be the height of that rectangle? 1/2. Area is length times width. And if the length is 2, the width of that rectangle, the short distance, would have to be 1/2, so the area is 1. So what is the equation of my density curve? Let me try answering this, or asking this in a different way. If you have a line going through the point 0, 1/2, and it is parallel to the x-axis, what is the equation of the line? Okay, y equals 1/2. Okay, we're going to the board. Going to try drawing a density curve. We're doing something that is really about this point in a, going to go over here a little bit more. This would be in a beginning algebra at about this point in the semester. Actually before this, maybe 3 weeks before this, like in the second or third week. Coordinate system. Okay, so x and y. You did this in the bivariate, just a reminder. Let's see, let's do this a little more systematically. I'll go out to here for the 2. So this is 2. This is 1. And therefore, this is 1, and this is 1/2. Now you're told that you have a constant height for this density curve between 0 and 2. So it's defining a rectangle for you. A horizontal line going through the point 0, 1/2. Must have the equation y equals 1/2. So your density curve is this. And is the area under my density curve equal to 1? Well, if I have the area of a rectangle, its length times width. Now, if you prefer to consider the width 2 and the height 1/2, I don't care which way you go. I'm just going to say it's 1/2 times 2, which is 1, and it satisfies that condition. Any questions? Okay, let's go back to the book. It says use your graph. Now, by the way, the only thing that irritates me about the notation in this problem is that instead of using the variable as x, it uses as what? Y. Frustrating. So if you'll allow me to translate with what I have on the board as we go back to that diagram on the board, if you would, Jennifer. I'm asking here for the probability that x is less than or equal to 1. So if I look at the problem, this region I have demonstrated here is half the rectangle, correct? So the probability should be 1/2, because it is going to be the area between 0 and 1 for that rectangle whose height is 1/2. So you say 1/2 times 1. I shouldn't use an x at that point, but I get 1/2, which you also know of as 0.5. I believe that is part C. Back to the document camp for a moment. That finish the problem? Right? Now, it would have been a whole lot harder if it had been a triangle, an isosceles triangle with a base of 2. Now let me ask that question to extend this just a little bit further. As we go back to that diagram, and I had a triangle with this base. And I wanted it to be an isosceles triangle. That means the two sides are equal. What would be the height of that triangle to make this work? I heard a 1 very quickly. Do you concur?
Yes.
I see 2 head nods. That means 3 of you are with me in this, and the rest are sinking. What is the area for a triangle? Okay, Daniel's saying 1/2 times the base times the height. And if my base is 2, do I have any choice for the height but 1 if the area is to be 1? That's the only way I'm going to get an area of 1. And what am I required to have under the density curve? An area of 1. So that means the vertex for this triangle could be where? That's going not too badly uphill. Where could I draw the vertex for this triangle? I said isosceles, but does it have to be isosceles? I could do this triangle, a right triangle. Would the area be 1? Yep. I could do this right triangle. Area is still 1. I could take the point for the vertex up here, right here, and now it would be what? An isosceles triangle, and that area would be 1. In fact, I can take that vertex for this other angle and put it anywhere in this line up to here. Now, I want to define x only between 0 and 2. Otherwise, I could go elsewhere. So this could be, although less easily done, this could be a density curve that I draw something like this, which is not going to be necessarily a right triangle. I have to be careful because it's looking very close to a right angle there. But I could have infinite number of triangular distributions with this base satisfying the property of that density curve. Finding the equation of those two lines is going to be difficult because the density curve is going to be defined into 2 pieces. So if I just take this one, we're thinking of test questions now. How would you define the density curve in 2 pieces? I've gone into intermediate algebra maybe, or a very serious presentation in beginning algebra. Sean?
0 to 1, it would be y equals x.
Okay, for 0 to 1, f of x equals x. This is y equals f of x. For x between what? 0 and 1. And it's equal to what? Okay, negative x plus what? 2. For x between what? A piecewise defined density curve. This reminds me a little bit of a homework problem that we looked at, or I looked at for you this weekend, in which you were looking at gas mileage, fuel consumption in essence, with speed. And in terms of a bivariate data analysis, this would be a positive association from 0 to 1, but a negative association from 1 to 2. And in terms of what you saw in some of the problems I graded in chapters 4 and 5, you would have considered this probably curvilinear or a strong relationship to a parabola. Okay, that was number 48. And I took it a lot further, but if I gave you the same question on a test for this isosceles triangle, what is the probability that x will be less than or equal to 1? Still 1/2. It's 1/2 of the area under the triangle just by observation. But I would expect you to say that you have 1/2 times the base times the height. This is going to be 1 up here. So you would have 1/2 times 1 times 1, which is 1/2. Any other questions on chapter 10? Any other questions on chapter 10? This is due this morning. Lisa? 14. Can you give me a page number, please? And I'll come back center on this as soon as we get a page number. 2 what? 259. Well, I keep going too far and not far enough. I keep bouncing around. And this was number 14? Okay. Have we seen this diagram before? Well, about 30 seconds ago. It's on the board. And I think it says verify that the area under this is 1. We just did that. Okay, so we've got it now. Good. Okay, other questions? 47. That's back around 268 again, where we just were. Unusual dice. Okay, there are various kinds of unusual dice. We had tetrahedral dice, right? And we could have non-standard dice, as this is talking about, sometimes referred to as what? Loaded dice. Don't want to use them in a craps game, but anyway, many random number generators allow users to specify the range of the random numbers to be produced. Nope, I'm supposed to be in 47 up here, unusual dice. None can produce interesting outcomes. You have 2 balanced 6-sided dice. One is a standard die having 1 through 6, and the other has what? 3 faces with a 0 and 3 with a 6. Is that correct? Okay. So, what are we supposed to do here? Find the probability distribution for the total number of spots in the same way you would roll 2 dice. Okay, so what are the possible values you can have if you roll 2 dice and you add up the points? So I'm going to let's see if I can. I'm just going to use this little space I have right here to the left of my diagram for the moment. As I go there, the idea is that and I don't know if you want to do this vertically or horizontally, but if you're going to get the distribution for the outcomes, and the value we're interested in is the sum of the pips coming up in the 2 dice, what's the lowest value you could have? 1. Do we agree with the 1? You get a 1 and a 0. Okay, what's your highest? 12. You get a 12, agreed? So we can have a 1, 2, 3, 4, 5, and 6 without any trouble, because we could get those on the first die and get what on the other die? A 0. Or we could do what? Go from 6 all the way up through 12. Agreed? I'm not feeling real good about the space I've provided myself. And one way you could do this is think of it in just listing all 36 pairs, correct? Otherwise, you have 36 possible outcomes, and you can just count there. Now, You're interested in the probability of X, correct? And am I asking the question correctly? I need to come back center for just a moment to make sure I'm asking the question correctly. Yeah, you want the probability of distribution with the total number of spots up on the two faces. So as we come back to this, how many of those would have a 1 on them? I mean, a 1 with a 0. Of the 36 possibilities, you can get a 1, and then you would have 3 other of the ordered pairs with a 0. So this would be 3 out of the 36, correct? Just thinking of 36 outcomes. That's one approach you could do to it. Okay, and how many ways could you do a 2? You can get a 2, again, with 3 other ordered pairs. So 336. Let's just jump to the 6. How many ways of getting a 6? Again, 3, correct? So what you might be arguing here is that every one of these values is equally likely with probability what? 1/12. A uniform distribution from 1 to 12. Could you do it as a tree diagram? Well, it wouldn't be so bad. Be better than the one we had in our study guide for 2 dice with each 1 through 6. If you do this as a tree diagram, let me just start that down here, you'd have 1 branch for the 1, correct? And then after the 1, you can get what? A 0 or a 6. Then for the 2, you can have what? A 0 or a 6. What's the probability for each of these 6 branches that are going to come out here? They're going to be each 1/6, correct? And what is the probability here? Of getting a 0 on the second die, which has 3 zeros and 3 sixes. 1/2. And what's the product of 1/2 times 1/6? The 1/12. Or I could get what? A 1 followed by a 6. And again, that's 1/12. Okay? And you can just see that as you go down. How many branches are there total? 12. Equally likely. So different approach. Is that enough? I'm 47. Any other questions? Any other questions in Chapter 10? Okay, I'll ask that that be turned in at the end of the hour this morning in Chapter 10. Okay, let me come back center. Thinking ahead to what we need to do this week, and I'm just going to go back here in a moment. Jennifer, give me a moment to go to the schedule to see what we have as an obligation time-wise. But we've done Chapter 10, Chapter 11, and I have Chapter 12 and Chapter 13. So let me come back and see where we should be in terms of the time. Okay. I need to bring that down here. Here we go. This is week 7. Chapter 10 and Chapter 13, I've reversed the orientation here in terms of what worked for me better this time. You'll notice we have 11 and 8. Now, 8 was simply on how you take samples. And we've talked about random samples, systematic samples, cluster samples already. And Chapter 11 and Lab 7 were what actually was involved. And then I covered 10 in this week here. So in week 7, I have Chapter 13 involved and Lab 10. So that's what we have scheduled for this week. And you'll note I don't have listed there Chapter 12, but I usually tie it together with what I've done in Chapter 10. And Chapter 13 is separate. So, with that said, Chapter 12 is simply an extension of Chapter 10. We talked about it last week. It is a generalization of two formulas. And I mentioned to you Bayes' theorem. But let me go to Chapter 12 briefly, just to put in perspective where we are going this week. This was the general addition rule and the general multiplication rule that was covered here. So on page 307, just to remind you of what we've already done, I need to talk a little bit more about this. But here was your general addition rule for the probability of A or B. Remember, if A and B are disjoint, these are events, and events are subsets of the sample space. But if A and B are disjoint, their intersection is the empty set. So when I go ahead and I look over here at this part right here, the probability of A and B, when A and B are thought of, we think of as A intersect B. If A and B are disjoint, the intersection is the null set, and this probability goes to 0. So if you have disjoint events, the probability is a simple version. The probability of A or B is just the probability of A plus the probability of B. This is the general one when A and B are not disjoint and the intersection is not the empty set. Remember, we did a Venn diagram to talk about that. So that's the general addition rule that I'm going to expect you to be responsible for. And then, related to that, there is a general multiplication rule that we have here. And this is on page 311. And remember, this notation right here is read as what? B given A. So if A and B are independent, then the multiplication rule for P of A and B is just the product. Probability of A, probability of B. But if A and B are not independent, then we get what we call conditional probability. And we talked about that with the tree diagram drawing without replacement from a deck of cards. There is a formula that we are going to generate out of this, coming back to the book for just a moment, and a good old-fashioned algebra effort. If you solve for the probability of B given A, divide both sides by the probability of A, then you're going to get what is on page 310 as we come off here for a moment. And here is the formula which is given for the probability of B given A. It's called the conditional probability. I'll get that over so you can see the B given A. And I reference you to the study guide on this. Note this is like a Schilling fraction, B over A, and the probability of A is in the denominator. I could have just as easily said the probability of A given B, and if I do, you'll have the same numerator, but the denominator will be the probability of B. I want you to be aware that the probability of A given B is not equal to the probability of B given A in general. Those three formulas you need to spend some time memorizing. They're easy to memorize. They should be part of your background. And I am going to select some problems out of Chapter 12. If I look at the, let me come back now to the computer in just a moment. If I can get it to do what I want, I'm going to go to the 4th edition homework assignments. And the connection here reminds me of something that happened with modems 10 years ago. There we go. In particular, I want you to note that there is an assignment of homework problems in Chapter 12 as we go to the homework assignments in the 4th edition. You might want to write these numbers down for Chapter 12 as you start looking at some problems in Chapter 12 as part of your homework along with Chapter 11. So you should be doing some Chapter 11 homework, and you might want to look at some of these early problems in Chapter 12, because I'm going to be spending time in Chapter 12 tomorrow talking about this homework assignment and some of the problems that are related to it. So if I look at 6 and 8, coming off there for a moment, and I'm going to go to the text for a moment now, problems 6 and 8. If I get to problem 6. Distance learning, and of course the video-based is a distance learning kind of problem. And here are some probabilities given to you in this problem, and let me bring that down tighter. You have the probability of A is 0.7, the probability of B is 0.25, the probability of A and B is 0.05. And then you want to find the probability that students, I want here the probability that the student is less than 25 years old, and then what is the probability that the student is at least 25 years old and not local? So that is, we're given information and you're supposed to find some probabilities. That's probably a good place to start. So we'll come back and look at number 6 and number 8 tomorrow. Number 8 is related, I believe, to the same distance learning problem in terms of conditional probability. So that's where I'll start tomorrow. Take time to maybe look at those two problems in Chapter 12. So Jennifer, as we finish up here, make sure, by the way, you sign the roll sheet. It's up here in about the 2nd row. But we had the Rolling Stones. What is your choice as we close? Moonlight Mile. Moonlight Mile. Doing your homework in the dark in statistics. Okay.